Welcome, everyone. Today, we're diving into mastering your science fair project with a step-by-step preparation approach. Let's start with the basics, understanding how to structure your journey effectively. Think of this process like building a strong foundation for your scientific exploration. Remember, every great project begins with a solid plan. As we move forward, we'll break down each step to make it both manageable and enjoyable. Ready to embark on this exciting adventure? Let's get started. Let's be real for a second. When you hear the word science fair project, your first thought probably isn't hooray. It's more likely another impossible assignment. And now you've got this fancy science fair template staring you down, right? Well, guess what? This isn't just another pile of homework. This is your secret weapon. Think of it as the ultimate blueprint for turning your genius-level ideas into an absolute judge-impressing masterpiece. Forget the boring stuff. We're going to hack this template and break down the whole process step by step. We're going to show you how to go from feeling stuck to being a certified scientist in no time at all. Are you ready to rock your research? Let's dive in. First up, the problem. Listen up closely because this is where most students, even the smart ones, mess up. A science project isn't just a topic. It's a testable question. You don't get credit for saying, "I'm studying video games," or "I'm researching recycling." To a judge, that's boring and way too big. You can't solve the entire world's recycling problem in one experiment. You need a laser-focused, specific question that you can actually answer with data. The rule of thumb? Always aim for the how does X affect Y structure. For example, how does the surface type affect the speed of a marble? Or how does the amount of sunlight affect the height of a bean plant? This structure immediately tells the judges you know exactly what you're testing. It turns a vague, messy idea into a clear scientific mission. Find your X, find your Y, and you're already ahead of the competition. Let's look at a classic example of turning a daily habit into a scientific investigation, the fast food myth. We've all been there, slamming an energy drink to get through a long afternoon. But have you ever wondered what that drink is doing to your body before it even hits your bloodstream? Our laser-focused research question asks, how does the concentration of popular energy drink brands, let's call them X, Y, and Z, affect the activity of amylase, the primary digestive enzyme in our saliva? Now, why does this actually matter? Because it hits on questions we all care about. Can these drinks actually make it harder for your body to break down food? If one brand is worse for digestion, is it because of the caffeine, the mountain of sugar, or those secret herbal ingredients? And finally, could this be the hidden reason you feel so sluggish after a big lunch and a Red Bull? This isn't just chemistry. It's about understanding the immediate impact of what we consume. Now picture this. You're in the middle of a high-stakes match. You hit the button and nothing happens. You're eliminated. You blame the lag, but is it your internet or is it the physics of your hardware? In example 2, we're looking at the gaming lag. Our laser-focused research question is, how does the physical distance between a wireless gaming controller and its receiver unit affect data transmission latency, measured in milliseconds? This project gets to the heart of what every gamer wants to know. Is my terrible reaction time actually a skill issue? Or is it because my controller is too far from the console? Is the lag linear? If I move twice as far away, does the lag double or does it get exponentially worse until the connection just drops? And the big question for our wallets, Do those expensive pro gamer controllers actually have the tech to handle distance better, or is it all just marketing? By the end of this study, we'll know exactly where the sweet spot is for peak performance. Your question should be testable. This means you can measure the results. Avoid yes or no questions. Aim for how does X affect Y. This sets the foundation for everything else. Next, the hypothesis. Think of this as the absolute most important sentence in your entire project. Why? It's your scientific GPS. It tells the judges exactly where you're going and why you think you'll end up there. It's not just a guess, it's an educated guess. That educated part means you have to back it up with research. Don't just guess. Use the classic powerful format. If, then, because. So, why is this one sentence so critical? First, it's your blueprint. It defines the relationship between what you're changing, the if, and what you're measuring, the then. Without it, your experiment has no focus. Second, it proves your research. The because statement is where you get to show off. It connects your experiment to real scientific principles. This is what judges crave, scientific reasoning. Finally, it's the final test. Your entire conclusion will come back to this one sentence. Did your data support or reject this exact hypothesis? That answer defines your success or your next big discovery. For instance, if I increase the salt in water, then the boiling point will rise because salt particles interfere with water molecules escaping as gas. See that? The because part is your chance to shine and show you know your stuff. Alright, let's talk about the absolute core of your science project, variables. This is the line between a good experiment and a great one. Think of your experiment like a movie. You need to control the setting, the actions, and the results. If you don't control them, your data becomes a mess, and the judges will spot it instantly. First up, the independent variable. Think of this as the I change. This is the superpower, the one thing you get to tweak. You're the boss here. Ask yourself, what am I testing? Just remember the golden rule, only one allowed. If you change two things at once, you'll be left scratching your head about what actually caused the result. Next is the dependent variable, or the data you measure. This baby changes because of your independent variable. It's what you lovingly record in your notebook. Ask yourself, what am I measuring to see the effect? This is your evidence, so keep it precise. We are looking for numbers and units. Think seconds, centimeters, or degrees Celsius. Finally, we have the controlled variables, also known as the constant cups. These are the rules, the things that must stay exactly the same for every single test. Ask yourself, what could mess up my results if I let it slide? If you don't keep these in line, like using a different pot or a faster stove setting, you might give the credit to the wrong variable. Theory is great, but let's see how this actually works in a real lab setup. We're going back to our salt and water experiment to see our variables in action. First, our independent variable, the amount of salt. This is the I change. You might test 0 teaspoons as your control, then 1 teaspoon, then 2. Notice how you're the one in the driver's seat, physically changing that measurement. Next, the dependent variable, the boiling temperature. This is the data. We aren't choosing the temperature. We are waiting to see what it becomes. Whether you're measuring in Celsius or Fahrenheit, this number depends entirely on how much salt you stirred in. Now, look at our controlled variables. This is where most students get tripped up. To keep this fair, you must use the exact same pot, the same volume of water, and the same heat setting on the stove every single time. Even using a different thermometer could throw off your numbers. Now that you have your big idea and your variables set, it's time to write the recipe for your experiment. This is the materials and procedure section. The rule here is simple. To get the respect of the judges, you have to be a pro and be precise. Think of your materials list as a shopping cart, but with strict rules. Scientists don't use some water or a little salt. First, speak the global language of science. Always use metric units. That's grams, milliliters, and centimeters. Second, be exact with quantities. Instead of saying salt, write 3.5 grams of table salt. If you don't list exact amounts, your experiment can't be trusted by other scientists. Next is your procedure, your step-by-step instruction manual. This is the most important part because it proves your experiment is replicable. Ask yourself, is this so clear that a student on the other side of the world could follow your steps exactly and get the same results? If a judge can't follow it, your experiment isn't valid. To pass the test, use a numbered list and start every step with an action verb. Don't be passive, be a director. Instead of the beaker is placed, say, measure 5 grams of sodium chloride. Pour 100 milliliters of water. Record the temperature every 30 seconds. Precision is the hallmark of a great scientist. Get your recipe right, and your result will be unstoppable. Once the experiment is done, you're left with a pile of numbers. But remember, while numbers don't lie, they need a serious makeover to be understood. Think of your raw data as the proof and your graphs as a story. To win over the judges, you have to be an amazing storyteller. First, let's look at your data tables. Your goal here is to organize every single piece of information you collected. Use your template to list your independent variable levels, like your salt amounts, and record the results for every single trial. Don't just show the average. Judges want to see trial 1, 2, and 3. It proves you did the work and shows them exactly how consistent your results really were. Next, we turn the table into a graph. A good graph tells a judge the whole story in under 5 seconds. Just remember the golden rule. Your independent variable, what you changed, always goes on the x-axis. And your dependent variable, what you measured, goes on the y-axis. Pick the right tool for the job. Use a bar graph when you're comparing independent groups, like 3 different types of soil. Use a line graph if you're showing a change over time or a continuous relationship, like water temperature rising every 30 seconds. Finally, the most important step, label everything. Give your axis clear titles, and most importantly, include your units like seconds or centimeters. Don't make the judge guess what they're looking at. If they have to hunt for the units, you've already lost them. You've got your data and your graphs. Now what? It's time to put on your detective hat and figure out what it all actually means. Discussion. This is the section where you show the judges that you don't just follow instructions. You think like a scientist. First, let's analyze. Don't just say the numbers went up. Look for the trend. Use math to explain the relationship. For example, did the lag double when you doubled the distance? Using percentages or ratios isn't just about sounding smart. It proves the significance of your results. Now, give us a reality check. Show critical thinking by admitting that no experiment is perfect. Identify at least 2 sources of error. Maybe it was human error, like starting a timer a half second late, or systematic error, like an inaccurate marking on a beaker. Judges love this. It shows you understand how real science works. Alright, future scientists, you've run the experiment, you've wrestled with the data, and now we've reached the grand finale, the conclusion. This is your final chance to take the stage and shine. We're going to wrap this up in 2 powerful steps. Step 1, the verdict. It's time to be brave and be direct. You must use the word supported or rejected. Now listen closely. It is 100% fine and honestly very common for a hypothesis to be rejected. In the professional world, a negative result is still a massive scientific discovery. The judges aren't looking for a perfect result. They're looking for your honesty and your ability to analyze what actually happened. Step 2, the big picture takeaway. This is where you move beyond the numbers. Don't just repeat your data table. Tell us what your finding means in the real world. Think of it like this. If you had to tell your best friend what you learned in just 1 sentence, what would you say? This is the so what moment. It shows off your critical thinking, and in a science fair, that is the real win. Summarize your journey, stand by your data, and be proud of what you've uncovered. You've done it. As you wrap up your final science paper, especially that all-important conclusion, take a second to look back at how far you've come. I want you to remember one thing. Your work is truly valuable. In science, the true measure of success isn't whether your hypothesis was supported. It's whether you follow the data where it led. If you find yourself writing the words, "My hypothesis was rejected," don't see that as a failure. That is a moment of triumph. You've just discovered a scientific fact, and that is a fundamental part of how we understand the world. You have completed the full cycle of scientific inquiry. From a spark of a question to a documented discovery, you've done the work of a real scientist. You should be incredibly proud of what you've built. Congratulations on your scientific discoveries.